Hi, everyone. So this is statistical reasoning in class activity or lesson 12C, confidence intervals for a population mean. So there are many situations where you might be interested in estimating a population mean. Remember, that means average. For example, you might be interested in collecting data from a random sample of students who graduated from a two-year college in 2020 to learn about student loans. If you asked each student in the sample the amount of their student loan debt, you could then use the data to estimate the mean student loan debt for two-year college graduates. So here's a question to think about. What are examples of other situations where you might want to estimate a population mean? So go ahead and pause the video and just write down a couple ideas. Welcome back. So again, this answer is going to vary. It just depends on what your discipline is. So, for example, if you're in criminal justice, you want to estimate the average salary for a state police officer. If you're in business and you want to see how like the Dover race impacts the local economy, you might want to find the average amount, a typical or average amount that a person would spend when they come to Dover for the race. So average amount spent. By a race fan in Dover during the race weekend. And it goes on and on. I mean, if you're in medical field or nursing, you might want to know the average duration somebody spends in the hospital with a particular disease or particular ailment. Okay, so let's move on. So objectives for this activity are, you're going to understand there are assumptions that should be checked to ensure that the one sample T confidence interval is an appropriate way to estimate your population mean. So again, in 12C, we're going to work with one population or sampling from one population. You're going to see in 12D, we're going to be sampling from two populations and comparing them. So this is a one sample T confidence interval. The relationship between the confidence level and the length of the interval. You will be able to assess whether the assumptions for a one sample T confidence interval are reasonably met. Calculate and interpret a confidence interval for the population mean. And then use technology to compute a confidence interval for a population mean, and also interpret a confidence interval for population mean in the context of the situation. So recall in lesson 10, you constructed confidence interval estimates already for a population proportion or percent, and a difference in the population proportions for two populations when certain assumptions or conditions were met. The form of those confidence interval was some estimate plus or minus some margin of error. In essence, that's how all confidence intervals are created. It's going to be an estimate plus or minus some margin of error. The same is going to hold here as well, where the margin of error is calculated by multiplying the standard error of the estimate by a Z critical value corresponding to the desired confidence level. So in the population you are interested in estimating is a population mean, the confidence interval has the same form. X bar, estimate plus or minus margin of error. In this case, is going to be X bar. The estimate used to construct the interval is the sample mean, X bar. X bar is an estimate for the population mean, mu. And that's ultimately what we're trying to determine is what is the value of mu for a given population so we can make a decision based on our discipline. And the standard error used is the standard error of the sample mean, S over square root of N. S is your sample standard deviation, N is your sample size. The margin of error is calculated just a little bit different. Instead of multiplying by the value of a standard error by a value from a normal distribution, it is multiplied by a value from the appropriate T distribution. So again, the T distribution is very similar to the normal distribution. You should have been exposed to the T distribution at this point. This is not surprising if you think back to work with your standardized T statistic from your last lesson, in class lesson 12B. The formula for a confidence interval for population mean for one population where you're taking one sample is X bar, your sample mean, plus or minus the T critical value from the T distribution times your sample standard deviation over the square root of your sample size. So X bar plus or minus the T score times S over square root of N. The T critical value, the T score in the data analysis tool is the confidence interval will depend on the sample size. The degrees of freedom for this confidence interval is going to be N minus 1. We talked about that in the last lesson. N minus 1 is the number of degrees of freedom at your sample size minus 1 and the confidence level. This interval is often called a one sample T interval. While you use technology to do the calculations, you can see from the confidence interval formula that you are just taking the sample mean and forming an interval around it by subtracting and adding the margin of error to get an interval of plausible values for the population mean mu. Okay, 2. The General Social Survey, GSS, collects data from a representative sample of adults in the United States on a number of attitudes and behaviors. And here's the link if you want to go learn more about it. One of the questions asked as a part of the survey is how many hours are spent watching TV on a typical day. The data set we will be using consists of responses from a sample of 1,555 adults from the 2018 survey. Describe the population mean that these data could be used to estimate. Be sure to describe your description includes the population of interest. Go ahead and pause the video for a minute and write down your answer to that. And we'll be back in a second. All right, welcome back. So this data or these data could be used to estimate the mean number of hours spent watching TV on a typical day for adults in the United States. So the mean number of hours watching TV on a typical day by the population of adults in the US. Okay, so now it asks us to go to the DCMP, the Data Center Math Pathways Inference for Population Mean tool. Again, you can do this one of two ways. Here's the direct link to the app that you need right in the lesson. You could copy and paste this into your URL in the browser and then go to this site. Or you can go to the Data Center Math Pathways Data Analysis tool, which has a list of all the apps that you're going to need for the course. You use this tool to calculate confidence intervals for population mean under confidence and significance tab. Okay, so let's go ahead and go there. So let me share my screen. Again, I have a bookmark for the Data Center Data Analysis Tools, which is a list of all the apps you've been using throughout the semester, and they're broken by category. So here's exploratory data analysis, categorical and quantitative. This is what you did way back in lessons 1 through 5-ish. Correlation and regression, you did a little bit of this in lesson 5A, and most of this was in lesson 6. Distributions, normal t-distribution, binomial, we kind of exposed those to you, like in lessons 8, 9, and 10. Central limit theorem and sampling distributions, this was earlier in the class. And now what we're going to be working on in 12C and 12D lessons are confidence intervals for one sample for 12C and confidence intervals for a sample, two samples in 12D. So the one they want you to use here is inference for a population mean. So you can see that this link right here is the same link that's in the lesson. If I click on this, it's going to bring me to that particular app within the data analysis tool pack. I'm going to pause just for a second until it comes up. Okay. So we're going to go from the textbook. It's already chosen that we're looking at TV hours. And that's the one they want us to look at. And that's the one that's in your lesson. So you can see a couple different things here. The data was from the textbook. We chose the data set TV hours. There's other ones there as well. Name of our variable is hours watching TV. And this is raw data. Here's the, if I extend it, here's all of the observations, all the 1,555 observations of how many hours a week a typical adult watches TV. I believe that's on a day, right? Typical day, sorry about that. So these people all watch TV today for 0 hours. These people all watched it for 1 hour and so forth. Okay. So you can see here's a histogram. It gives you the distribution. So most people are watching right around 2 to 3 hours. That's your peak. And there are some outliers that somebody today actually watched 24 hours of TV out of the 1,555 people. So let's talk about this area right here and some of the options you have over here. So here's your descriptive statistics. Again, this is just your little n, your sample size is 1,555. The average of all those 1,055 values is 2.938. That's your average number of hours watched for TV. The typical deviation is 2.837 hours. So generally people are watching TV for this many hours, plus or minus that many hours. The point estimate is X bar. Your sample mean is your point estimate. That's the guy we're going to add and subtract to form the interval down here. The typical error is your standard deviation, 2.837 divided by the square root of your sample size. So if you take this value and divide by the square root of 1,555, you'll get this standard error. The t-score, remember, comes from your t-distribution, and that's dependent upon your confidence level and how many degrees of freedom you have. In this case, when your sample size is 1,555 for one population or sampling one sample from that population, we lose 1 degree of freedom. So your degrees of freedom is 1554. And if you go back and you go to that distribution, you go to your t-distribution and bring that up. Hopefully it'll come up quick enough so I don't have to pause the video too much. Okay, so we can find probabilities. And if I have degrees of freedom 1554, and I want to have a two-tailed, where I would look at the probability in the middle or on either tail, and I want, I'll show you the number we just used right there, 19615. If I type in 1.9615, hit enter. You can see that's 95% in the middle. So you have to go out 1.9615 deviations in a t-distribution with 1554 degrees of freedom to capture 95% of the distribution. So you can see 2.5% is on the high side, 2.5% is on the lower tail. So that's 5 total percent that won't be captured. Okay, so that's where that number comes from. So if you adjust this, it automatically calculates the t-score that you're going to be required to multiply by your standard deviation. These two values multiplied for this type of interval is called your margin of error. And it's this that we're going to add and subtract from our point estimate to produce the confidence interval. So when you take 2.938 and subtract 0.1411, you get 2.797. And when you take 2.938 and you add 0.1411, you get 3.079. So this is your 95% confidence interval. So based on our data and based on our analysis, we feel we're 95% confident that the average number of hours a typical adult in the United States spent per day watching TV is somewhere between 2.797 hours and 3.079 hours. So that's the interval right there. So let me go back to the lesson. Let me stop sharing. Okay. So it says, based on the output, what is the 90% interval? So I was showing you the 95%. So I'll go back and show you the 90%. Let's share the screen. So if I come over here and this is your confidence level, if I move it down to a 90% confidence level all the way down here, notice the t-score changed, 16458. Again, if I show you in the distribution of type in 1.6458, you can see 90% of the distribution is captured between those two t-scores. 5% is still left on the upper tail and 5% is still left on the lower tail. So 10% of the time we're using a technique that doesn't work. So we're only capturing 90% of the distribution. And that's the t-score that corresponds to that. So this is what's in your lesson plan right now, the 90% confidence interval, where the lower bound is 2.82 per hours and the upper limit is 3.075 hours. So let me go back again. So they already had this in your lesson. So the 90% is all of this information was what I just showed you on the screen. So based on the output, what is the 90% confidence interval for the mean number of hours spent watching TV on a typical day for US adults? So the lower bound, when you write an interval, you always want to use a left parentheses. Put the lower number on the left side, 2.28. And on the right side, you put the upper number, 3.057, I believe that says. And then a right parentheses. This is how we write an interval mathematically. Okay. So question C. Think about how you previously interpreted confidence intervals for proportions. How would you interpret the confidence interval you just calculated? Again, this was a 90% confidence interval. So for this one, we're going to say we feel 90% confident that the true population mean mu of all adults in the US spend between 2.28 hours and 3.05 hours per day watching TV. Okay. So again, either the mean is in here or it's not. Again, how we interpret this, we feel 90% confident. We've just used a technique that works 90% of the time. Whether or not the mean is in here, we're not sure. 90% of our intervals, when we compute this, will have the mean in there, and 10% will not. Okay. So the probability is not 90% that it's in there. It's either in there or it's not. We're just using a technique that works 90% of the time. So now it asks you, which of the following is the correct interpretation of the level 90%? The probability that the actual value of the population mean is between 2.82 and 3.057 is 90%? No. 90% of adults in the United States watch between 2.82 hours and 3.057 hours on a typical day. No. If this method was used to construct a confidence interval for the mean for many different samples from the population, about 90% of the intervals would contain the actual population mean. Yes. That's how you interpret 90%. In other words, if you use this technique over and over again, 90% of those intervals would actually have the mean inside of them, and 10% would not. Whether or not this one does, we won't know. The only way we would know whether this was correct or not, and the mean was in between these numbers, is if you sample the entire adult population in the United States. And remember, that's not feasible. It takes too long. It costs too much money. It's just physically impossible to do that. The last one, which is also incorrect, says the mean number of hours that the US adults spend watching TV on a typical day is guaranteed to be in the interval. No, we're not guaranteed. We're only using a technique that works 90% of the time. Okay. If we were to use the sample to calculate 95% confidence intervals rather than 90% confidence interval, how how would the width of the two intervals compare? So again, I'll go back to the app on the screen and show you that if you increase your confidence level to 90, from 90 to 95, your t-score is going to be a lot bigger, because in the t-distribution, to capture 95% of the distribution, you have to go further out. So it's going to, a bigger confidence level is going to be a bigger t-score, which is a bigger margin of error, which makes the interval wider. So watch what happens when I make it 95%. The interval got a little bit wider. Okay, so let's go back. If you're to use the same, the sample to calculate 95% confidence intervals rather than 90% confidence intervals, how would the width of the two intervals compare? The width of the two intervals will be the same? No. The 95% confidence interval would be wider than the 90% confidence interval? Yes. So higher confidence, wider interval, because they have to go further out to capture that much more of a percent. Confidence interval, 95% confidence will be narrower than 90% interval? No. So again, if you want more confidence, you have to go further out in the distribution, which would make the interval wider. Okay, so now it says use the tool to compute the 95% confidence interval. Is it consistent with your answer in part E? Explain. So here's the results. We just showed you on the screen that the confidence interval for 95% is 2.797 to 3.079. Okay. So if you compare this to your answer before, yes, the interval widened. So is it consistent with your answer in part E? Yes. It is a wider interval. Okay. All right. So as was the case with the previous inference methods, there are a few assumptions or conditions that you should check before using the one sample t interval. The two important ones are the sample is a random sample from a population of interest, or it's reasonable to regard the sample as if it were a random sample. It is reasonable to regard the sample as a random sample if it was selected in a way that should result in a sample that is representative of the population. So again, as long as you're using a sampling technique that's not biased and appears to be representative of the sample, that's your first condition. The second condition is the population distribution of the variable that was measured should be approximately normal, or your sample size should be large enough. Usually a large enough sample for a mean is size 30 or more. So 30 or more is considered to be a large enough sample size. If the sample size is less than 30, then again, you should look at the plot of the data, dot plot, box plot, or if the sample size isn't really small, a histogram, to make sure the distribution looks approximately symmetric and there are no outliers. Okay, so the one we just did was 1,555 adults. That's way more than 30. So that satisfies the condition that the sample is large enough. Only when the sample is small, less than 30, do you have to guarantee that it looks somewhat symmetric, somewhat of a normal distribution. Okay. For the TV hours example, the sample size is large and the sample was selected to be representative of adults in the United States. So the one sample t interval is an appropriate way to estimate the population mean. Okay. So now let's go on to another example. Researchers in New York carried out a study to investigate how many calories are consumed when people eat lunch at fast food restaurants. They asked people eating lunch at different locations of McDonald's, Burger King, and Wendy's if they would give them the receipts after they had ordered, and they used the receipts to see what had been ordered to determine the number of calories in the meal. A total of 3,857 meals, which is way more than 30, were analyzed in the study. And the researchers believe that this sample was representative of lunch meals eaten at fast food restaurants. So there's your other condition. So it's representative of the entire population, and it's at least 30. so we don't have to worry about the distribution being symmetric. So both those conditions are satisfied, so it's okay to proceed. The mean calorie content for the sample was 857 calories, and the sample standard deviation was 677 calories. Is the 1T interval appropriate way to estimate the mean calorie content of fast food lunches? Recall that in the previous assignment, you decided the population distribution of calorie content for fast food was not normal. That's okay because our sample size was larger than 30. It's 3,857, which is way larger than 30. Are the assumptions for the one sample T interval reasonable? And the answer is yes. First reason is because it said the sample was representative of the population. Yes, the sample was representative of the population. And two, was the sample size at least 30? And if it was not, was the distribution somewhat normal to begin with? Well, our sample size is 3,857, which is much more than 30. So, and our sample size is large enough. So there's your two conditions satisfied. Now it says use the tool to calculate a 95% confidence interval for the mean calorie content of fast food lunches. Go to the DCMP inference for population mean tool, the same one we just did, under confidence in significance test tab. Okay, so let's go ahead and do that, and I'll show you how you have to enter this information. So again, the sample size was 3,857. The mean was 857, and the standard deviation was 677. So let me share the screen with you. Okay, so there's three ways you can enter data. One of the ways is from the textbook. In other words, there's already a data set that they want to refer to, and that's what we did with the TV hours. And the other two ways are you can either enter your own data, but this is where you enter it individually. So I'd have to enter the 3,857 different calories for those people that ate lunch, for those adults. The other way, so again, this is the way you just type in individually. So if I was doing like people's ages, say at Delaware Tech, ages at Delaware Tech, I could enter person was 19, person's 19, 20, 21, 25. And as I'm doing it, it's generating all the analysis over here in the confidence interval. That's entering in one value at a time. The other way is if you already provided the summary statistics, then you can just enter the summary statistics. And that's what's going on here is they already told you the mean and the standard deviation. So the name of the variable is caloric intake, I guess, calories. Here's where your sample size goes. This is 3,857. Here's where your sample mean goes, 857. And here's where your standard deviation goes, 677. All you have to do now is select the correct confidence level. We want 95% confidence. So again, here's the summary of all the information we need. Sample size 3,857, sample mean was 857, standard deviation 677. That's just reiterating what you typed in there. The point estimate is always your sample mean, that's X bar. And from X bar, we're going to add and subtract this margin of error to produce this confidence interval. The margin of error, remember, is calculated as your standard error, standard deviation divided by the square of your sample size, that's your standard error, times your t-score. The t-score comes from the t-distribution. Okay, so 10.9 times 1.9606 is 21.37. So the actual interval down here is already completed for us. 857 minus 21, you always want to do the minus first to get the lower number, is 835.6 calories. And 857 plus 21.37 is 878.4 calories. So there's your 95% confidence interval for people eating at the fast food restaurant. So let me go back to our lesson. So here's the actual information summarized. Just copy and paste it into our document. Interpret the confidence interval from part B. So the interval right there again was 835.6 to 878.4. So because we're using a 95% confidence level, we are 95% confident that the mean or average, whatever you want to refer to it as, most people are going to call it mean to be consistent with the author, that the mean number of calories consumed by adults when eating at a fast food restaurant just abbreviate that, is between 835.6 calories and 878.4 calories. Okay, so again, we're using a technique that works 95% of the time. We sampled 3,857 adults. There's literally hundreds of millions of adults in America. But based on this sample, we're projecting on the population that the average adult, when they visit a fast food restaurant, consumes somewhere between 835.6 calories and 878.4 calories. An article that appeared on the website Global News indicated the following statement. Although every person's daily caloric intake is individual based on their personal goals and needs, nutrition experts estimate the average daily consumption at each meal should be broken down as follows: 300 to 400 calories for breakfast and 500 to 700 calories for each lunch and dinner. Snacks should not exceed 200 calories. Do you think your confidence interval in part B provides evidence that the mean calorie content of fast food lunches does not meet the recommendations in the given quote? Explain. Well, because lunch and dinner should be between 500 and 700, and this entire interval is above the upper limit, 700, it's evidence to suggest that eating at a fast food restaurant, you're consuming more calories than is recommended. So you could write this up any way you want with your own words. So again, the confidence interval, and I'm just going to abbreviate confidence interval, estimates the calorie content to be between 835.6 and 878.4 calories. Both ends are above the 700 calorie range, both of these endpoints, or you can say the entire interval is above 700. Both of these endpoints are above 700 calories. Therefore, these fast food lunches do not meet the recommendations in the given quote. Therefore, the mean calorie content of fast food lunches does not meet the recommendation in the given quote. The recommendation in the given quote. Okay, I hope this helps you, and we'll see you when you get to lesson 12D, when we look at estimating two populations and the difference between two means in two different populations. All right, take care.